Regular lecture now. Just so you know, we'll try to hand back exams as soon as we get them back. I was hoping to have them Thursday, but we didn't have them Thursday. But we have them for today. We handed them almost all of them back. If you were a little slow getting up here, don't feel badly. But next time, move a little faster. And today, we'll try to dismiss a few minutes early and get to you guys that missed out the first time through. So if you're here and you want your printout, that'll be good. Now, I want to go over a couple things with you concerning the printout. So make some notes. A couple things here I want to emphasize to you. First of all, your Exam X score is what you have on that printout plus what you have for clicking. Now, the clicking I published inside the grades page, I don't know, Sunday maybe? Yesterday? All right. So that is up, plus what you got here, and then I'll add them up, and you can mentally add them up yourself if you have your grades page open right now. And that's the sum, all right? Also, the percentage value on your printout is not accurate. The raw points, is that what it's? You made a paper airplane out of your... I don't think I'm getting through to you guys. So. One of the students up here made a paper airplane out of a printout. Nice. Anyway, I think there's the very last column. It says raw points up at the top, right? Okay, that's accurate. That's your test points. But the percentage is not accurate, all right? Because that's the percentage of 46 questions. But your exam was 50 points, 4 of them from clicking. And the Scantron machine over there in the College of Sciences building knows nothing about our clicking, all right? So that percentage is not accurate. The raw points are, and that's going to be one of the three columns for Exam X. There's going to be the clicking column, or the clicking row, the Scantron row, and then the total for Exam X. All right, and the first two numbers will add up to the third number. All right? I want everybody unfold your paper airplanes and look carefully at your printout, and I want you to look to see if you have any double answers. You know, and usually what that is, you bubble in letter B, and then you decide, no, I think it's actually letter D. You erase B, but you didn't erase it really well, so the Scantron machine thinks you have both of them bubbled in. Right? Now raise your hand if you have a double. Anybody else? All right. Now, I want you to look to see if you have any that are blank. A blank doesn't have any answer, and that happens when you don't bubble it in dark enough. All right? Does anybody have a blank? All right. All right, now one guy with a blank and one guy with a double, bring them up right here. And what I'll do tomorrow during office hours, what we have to do is dig your Scantron out of the pile and then figure out if you really did have two answers. If so, it's wrong. But if I can clearly see what you erased and what you wanted to answer, and if it's right, I'll change your answer by 1. And it's the same for you. I'll see if you have something bubbled in, okay? And hopefully I'll have it for you. Give this back to you. One more over here. Okay. Will, can you, great. Yeah, I'll take care of this. I'll try to get this done during office hours tomorrow. Can you put this on top of everything else? All the printouts, put them in alphabetic order. You don't have to. You can do it after. just one big pile. It's a pretty small pile. And then just, and put that folded sheet of paper on top. Just put it on top there. Okay, so we'll try to get that done. A few of you had a printout that initially said unknown student, and then we figured out that it was you. All right, and that signifies that you messed up your PID. And I saw one guy, he bubbled in a 3 that was supposed to be a 0. Okay, and I know it happens, but try to be careful with that. And most of you did fine on that. But try to avoid that in the future, and you'll get a printout with your name on it instead of unknown student. A student in the first hour said, "Hey, Dr. B, I've been looking at my grades for your class, and I thought it would show after a while, but my overall grade states that it is disabled. I just want to know how well I'm doing in the class in terms of assignments, tests, and attendance, but I'm unable to." Now, that student texted me that message this morning, and I said, I want you to ask, it was in the morning section, and I told him, why don't you ask me that in class? And that way I can answer in class so that everybody can know. He was referring to the little gray rectangle down at the bottom of the grades page. And in some classes that you have, history class, for instance, you may have a percentage down there, and you look it up and you say, oh, I have an 82%. Or, whatever your percentage is, 93.5%. The problem with that is that percentage is misleading, because I cannot program our grading scheme, our grading method. Best 2 out of 3 now, midterms. 45 points for participation. I can't program that in to web courses, because Canvas doesn't permit anything except what Canvas does, and Canvas has a very simple-minded grading thing, and the only thing you can do is disable it. Used to be you couldn't even turn it off, but now you can disable it, and that's what I do. It's because it's either Canvas's way or the highway, and I choose the highway because I don't want you guys to be misled. But if you're concerned about your grade, here's what you can do. Keep a track of your exam, okay? And I'll be publishing your Scantron, the Scantron line this afternoon right after class. And eventually, I think later this week, I'll do a roundup of clicking and give you an estimate of how many answers you've typed in out of how many possible, and how many you've gotten correct out of how many possible. And that way you'll be able to determine your clicking grade out of 45. And if your percentage on how many you've answered out of how many possible is above 85%, ching, just write in 45 points. And then divide by 95, and that'll give you, we got 10 homework points. So divide by 105, and then you'll know, add in your homework points, your homework score, and then add in the 45, and then whatever you got on the exam, and then that'll be some number out of 105, and that percentage will allow you to figure out your grade status at the present time. So everything is in there, everything will be in there, and everything except the clicking data is in there. And I'll try to get the clicking data in there, and when it is, then everything will be in there that will allow you to calculate your own grade percentage, and then look it up on the grade scale. All right? So it's not going to show the percentages that Web Courses provides for you, no matter where they are. For my class, for astronomy, ignore them. Okay? They are not accurate. I don't think I could turn off all of them, but of what I can turn off, I've turned off as much as I can. Kayla.
For the extra credit at the observatory,
I haven't, the question is, how many points for visiting the observatory? Which, by the way, can somebody look that up, actually, right now? What is it?
Tomorrow, they rescheduled last Thursdays for tomorrow.
Right, so what color is it?
It's still
Purple?
They don't say anything until the day of.
Yeah, all right, so keep alert for that. And if it goes green tomorrow, everybody go. If you could clear it on your schedule for tomorrow night, you just go. And I can't remember, Kayla, how many points I traditionally give, if it's 10 points or 5 points, but I'll look it up, and then that's how many you'll get. And what they do, just so you know, you go there, and the session is actually run by students that are members of the UCF Astronomical Society. They run the telescopes, okay? And they will give you a little handout, two-sided, and you'll put your name and the date and what section you're in, I think, or who your instructor is. And then in the rest of the printout, the handout, you'll write down your observations. You know, the rings of Saturn, probably you'll be looking at that. Albireo, the brightest, or I think it's the brightest star in the constellation Cygnus. They told me that you'd be looking at that. It's a double star system. Possibly the Andromeda Galaxy, if it's clear. It always depends on the weather. And you'll be making little sketches and notes about what you see. And then when you're done, before you leave, you give it to the UCF Astronomy Society, you know, one of the assistants there. And they'll round them up. There'll be lots of people, you know, not just yous guys, but other sections. And it's actually open to the public. So I know one time I was there, there's a whole troop of Boy Scouts, 40 or 50 Boy Scouts running around. I love going to those sessions. It's a lot of fun. It's kind of pandemonious, but it's fun. Anyways, you hand your printout, your handout in, and then they give it to me, you know, the week following, you know, and then I put it in the grade book, and, you know, you get your pointage. All right? Another question? You can go more than once, as I've mentioned before. And the reason for that, I want you to go. You can learn more astronomy in an hour and a half at the observatory, actually looking at stuff and thinking about it, than listening to me blab my big mouth for 3 hours a week for 14 weeks. All right, so I want you to reward you for going as many times as you're... And if you can't go, then, you know, God bless you. But we will have other bonus point opportunities, so don't feel like you're going to miss out. But as many times as you can go, yeah, I want you to go. There's a question over here. Go ahead.
Yeah, so since tomorrow's the first time that we can possibly go to the observatory, how do we prove that we were there too?
Oh, my gosh.
You prove it by listening in class to the last 5 minutes of what I just said. You'll do... Did you hear me? Did you hear me talking about the printout? What's that? No, man, you give it by hand. It's a piece of paper. And you give it to the guy at the observatory, and then he gives it to me. He puts it in my faculty mailbox. I'll have a big, thick stack of them. So it works good. Don't worry. Just go and do what they tell you, and be astounded by the beautiful stars and planets that you see. And then turn in that paper, and everything will be good. All right? Another question. Desiree.
How long does it normally last?
How long does it normally last? It usually lasts maybe an hour, 90 minutes. But you know, those guys will be there all night.
Yeah.
And if you want to go, just dress warm. And even, it's not going to get below 70, but it might feel a little chilly later in the evening. But if you want to stay there as long as they might be there past midnight looking at stuff. Because they're kind of astronomy nerds, and so you're almost an astronomy nerd right now. So, if you feel like going and staying, you just tell them, "Can I stay?" And they'll say, "Yeah, okay." Yeah, they love it. Yeah.
So this is kind of a weird question, but I've never done any of these things before. But is it outside? Are there
I should worry about?
Is it outside and are there bugs you should worry about? Yes, there are bugs. Well, I don't know, mosquitoes maybe. But, you're not going to be rolling around on the grass. But they will have, they will have 3 or 4 small amateur telescopes set up outside the observatory on the, they have a big grass lawn out there. And one of them will be looking at Saturn, and another one will be looking at the Andromeda Galaxy, and another one. And then they'll have the big one up in the observatory itself, and that'll be looking at different really deep sky objects. So you'll have several stations to go to, okay? But the only bugs and pests you have to worry about are mosquitoes, stuff like that, and bumblebees, I guess. Well, bumblebees come out during the day, so. All right, any other questions? Yeah, so hopefully, and if they go green tomorrow night, even I might show up. And if I show up, no, that'll be me. When I see you guys out there, it just cheers me up. You have no idea. So I'll be cheering for you guys. Okay, last comment for you is the end of the day today, the end of lecture is the official halfway point. End of the... Why are you You guys, no, come on. Anyway, 14th lecture today out of 28. And so, but don't forget, we lost 3. That's over a week. Okay, wise guy. Anyways, we lost over a week and a half. So we're not quite as far as we want to be. But anyways, today formally is halfway. So we'll have more lectures the second half than the first half, of course. But that's the way it goes. That's the breaks, as they say, especially here in Florida. All right, let's keep going with chapter 7. A couple more comments I want to review with you. We did talk about for instance, the mass of the solar system and its various components last time, and we concentrated on Saturn being 1/998th the mass in kilograms of the SUN. And some more comments from chapter 7. There's 5 other planets that were known to the ancients, in other words, to like the Babylonians and the ancient Greeks and the Egyptians and stuff like that. Mercury, Venus, Mars, Jupiter, and Saturn. And those are all like ancient gods of the ancient Greeks and stuff too. So two of the 8 planets were discovered in the late 1800s. And I think actually Pluto was discovered it's no longer a planet, but Pluto, Uranus, and Neptune were all discovered because of small perturbations in the orbits of Jupiter and Saturn. And they saw that, there's a little bit of a lag for Saturn and Jupiter at various parts of their orbits. And so somebody worked it out and they said, you know what, there's got to be a planet. And they worked out where it ought to be, and they went looking and they found the very outer planets, Uranus and Neptune. All right. So those were discovered by the telescope. The vocabulary term, the 4 closest planets, Mars, Earth, Venus, Mercury, they're known as the terrestrial planets. And they're marked by this feature. They're mostly rock and metal. Now metal, when I say metal, I mean iron and nickel core, like for the Earth. And the moon is also very similar to the Earth in composition. And then the core is metal, iron, and nickel for Earth. And then the mantle, the cladding, the outer covering, many hundreds of kilometers thick, is like silicon, oxygen, calcium, sodium, a lot of the heavier elements, but not quite as heavy as iron and nickel. And those form rocks, especially with oxygen. Silicon or silicate minerals form most of the rocks in the mantle and the crust of the earth. It's actually kind of amazing. Right? So the 4 inner planets are typified by that composition. And I love this picture. This is from chapter 7, and it shows the 4 outer planets, Jupiter, Saturn with the rings, and then the 2 blue ones, Uranus and Neptune. And then down here towards the bottom is good old planet Earth. Right down here, this little guy down towards the bottom middle. Whoa, it's pretty tiny. It's pretty shrimpy compared to Jupiter. And of course, Jupiter is pretty shrimpy compared to the sun. So there's a whole layer or a whole order of sizes where, one thing is big to one order and it's shrimpy to another order. So Jupiter's gigantic compared to Earth, but shrimpy compared to the sun. And the sun is shrimpy compared to other stars, like Betelgeuse. Betelgeuse is ginormous. It's a big red giant. And actually, I think it's a supergiant, if I recall correctly. And we'll get to Betelgeuse later in the semester. Some more comments. Comment number 3 for today. Next 4 planets, Jupiter through Neptune, are much larger and composed primarily of lighter ices, liquids, and gases. They're more like vast spherical oceans with much smaller, denser cores. Now, the word ices, I want you to emphasize that in your notes. When an astronomer talks about ice, plural, ices, he is thinking not just about ice in the slushy at 7-Eleven, or what do they call that? The Slurpee. Okay? And if you drink it, you get your nose starts to hurt. Does that ever happen to you? You get what do they call that? A brain freeze, a brain cramp. Anyways, so that's ice, that's water ice. But for an astronomer, he's also thinking carbon dioxide. And we have dry ice, you can buy it at Publix. But in the order of the solar system, there's tons of dry ice, carbon dioxide ice in the outer planets, and there's a lot of dry ice, carbon dioxide ice on Mars as well. He's thinking methane ice. And we can see that in the outer planets. We can make methane ice here on our planet. It's not that easy, but we can freeze methane. It's part of natural gas. We can filter it out and make compress it down and condense it and stuff to a liquid and then keep refrigerating it and get it down to a solid, methane ice. He's also thinking about ammonia ice. All right? And NH3. NH3 ice, we can see that in comets and stuff. We can see methane ice in comets, CO2 ice. We see all that stuff. We can see the spectral lines. And a lot of those ices, the spectral lines are in the infrared. But yeah, we can see them definitely. Question. What is your name again?
Hannah.
Hannah, right. Question.
So this might be kind of a weird question, but since the last 4 are, I guess, called like the gas giants,
Mm-hmm.
if you were to have a spaceship that could do this, would you theoretically be able to fly like through the planet and not like hit anything solid?
Hannah asked, theoretically, could you build a spaceship that could fly through the planet and out the other side? If you went straight through the center, the answer is no.
Really?
Because it has a solid core. And we think that at the core of those outer 4 is a metallic rocky core like Earth and like the terrestrial planets. Now, for the terrestrial planets, that's all we've got. But for the outer planets, we think that they have a rocky core, rocky metallic core. So if you were, if you kind of aimed, if you dipped, and so that you were, instead of digging through to China, you just dug through to San Francisco, yeah, maybe you could, and we've sent, we recently sent the Cassini spacecraft into the outer layers of Saturn. We didn't figure it would go very far, and it didn't, but yeah, theoretically you could fly through pretty deep into the layers of some of these outer planets, but it'd be kind of cool, But some people think that in Jupiter, the upper atmosphere of Jupiter, that life is possible. Things that float in the upper atmosphere, like almost like jellyfish floating in our ocean. Would that be creepy or what? Or it'd be cool if you could find them. By the way, this is a nice figure. It's actually from chapter 3. When you guys hopefully go out to the observatory tomorrow night, I don't know which version of Saturn you will see, because it depends on what part of its orbit it's on and what part of our orbit we're on, as to whether you see the rings from the edge view at the bottom left or almost tipped up, because the axes are not quite aligned. The axis of Saturn is a little bit dipped away from the North Star. And most of the other planets are as well. So you may see the top one or the bottom one or somewhere in between. And your UCF Astronomy Society guys will brief you on that. Question?
Why is it that the rings form like that and they don't just form like a sphere around?
Why do the rings form as rings and not as a sphere? The answer to that is angular momentum. The solar system was originally spinning. Just like, we look at galaxies and they're like a spinning pinwheel, disc shape, and they have spiral arms and stuff. We think the solar system looked a little bit like that, only ultra miniaturized. And so when things are spinning, they tend to flatten out like that. All right? But another comment. The sun has the same hydrogen-dominated composition as Jupiter and Saturn, and therefore and this is a reading question in the homework, it appears to have formed from the same reservoir of material. And that's what I just alluded to. When the solar system was first forming, the solar system, we think, formed from the smithereens and debris of exploded stars, supernova detonations, in way back billions of years, and all those debris floated around in space, and eventually, a blob formed that was a little bit more dense, and then it started to self-gravitate, got a little bit more compact, and as it did, it had bumps in it, and that bump caused a wobble, and the wobble became a spin, and that spin is still seen in the spin state of most of the planets and the sun. The sun, the spin axis of the sun is pointing pretty close to the North Star. All the other planets, except for Venus, the Venus is pointing almost directly away from the North Star. Nobody knows why that is. It's almost like flipped. It might have started pointing at the North Star, but for some reason it flipped. We don't know why. But all the other planets and the rings of Saturn and most of the moons are, orbiting the same, or spinning the same way. Oops, wrong way. So nearly all the oxygen present is chemically bound with hydrogen to form water, H2O. And that is significant for us for a bunch of reasons. Exoplanets, which we'll try to start talking about on Thursday, and a huge, huge topic. Planets that we have discovered, thousands of them now, orbiting other stars, and we're always looking for water, the signs of water. And we're also thinking about water when we look at other celestial objects. So add to your list here, not just exoplanets, meteorites that fall to Earth from space. We analyze those for water. Matter of fact, I was looking at one that they recovered from Northwest Africa, somewhere in Morocco, and they looked at the water content of that. They cut a slice of it off, and they analyzed the H2O that they found, little teeny molecules of it, and they checked the oxygen isotopes in there. So meteorites, exoplanets, meteorites, comets, asteroids, and of course the planets as well. All right, so we want to know about water more than just about anything else. Question?
Are exoplanets anything that revolves something other than our sun?
Yeah, an exoplanet exo means exterior or out of. So a planet outside of our solar system. And
We can see that kind of detail around the
we can't resolve them with even the Hubble can't, not even the closest to but what we see are the signs of the planets. When a planet goes in front of a star, the star will dim slightly. That's how we tell it's there. And also, when a star goes orbiting around a star, it'll actually cause the center of mass to go backwards and forwards, and we catch that in the Doppler shift of the spectrum. Like H alpha goes a little bit redder than usual, a little bit or more orangey than usual, and it oscillates back and forth. That's called a spectroscopic exoplanet. We find it spectroscopically. I'll be talking more about that Thursday and next week.
So they're technically theories because you can't really prove that they exist.
No, we know that they're planets. Yeah, we don't have a really good eyeball on them, but we know that they're planets. They're much smaller than the star, and some of them we can actually see in infrared. I guess we can see a little blip, if we look at in infrared sometimes. But usually we see it because it eclipses the parent star, or it causes a Doppler shift in the, like H alpha and other wavelengths, which I'll talk about next week. Let's talk about terrestrial planets for a few minutes. And what we're going to do is, this is a picture of, look at this picture of Mars. That is a high quality NASA image. See that gash going left to right across the middle? That is a huge canyon. And I've heard people say that from one end of that canyon to the other is like from New York to San Francisco for distance. Now, raise your hand if you've ever been to the Grand Canyon out in Arizona. Man, I've never been there, but I heard it's amazing. The Grand Canyon is a blip compared to this canyon. That's called Valles Marineris, the Valley of Mariner. It was discovered or observed by the Mariner spacecraft. And if you've ever heard of that famous H.G. Wells novel, The War of the Worlds, and they made it into a couple movies. One of them back in the 60s, and one of them just a few years ago with Tom Cruise, and boy, are they scary. And that book was written before we knew what this we could kind of see it. We knew that there was some dark region, a couple dark regions there. We didn't know what they were. And one of the observers was Italian. And he said, he used the word, is there anybody here that speaks Italian? You speak Spanish? No, man, Italian. Anyways, this guy, Schiaparelli, he was observing it, and he used the word canali. I think it's C-A-N-N-A, not cannoli. That's cannoli. That's something you eat. Canali is I think means channel or group. And so Americans thought, ooh, canals. Like the Erie Canal. And they thought, ooh, Martians, they've built canals on Mars. And so there's all this science fiction. And so this H.G. Wells thing was about life on Mars that they thought, and now we know that it's just dry as a bone. But it was formed by flowing water eons ago, and it's ginormous. So the canali, the canals, are actually, this is the main one, the Valles Marineris. Now let's take a look at the distinguishing feature, and that's something called the frost line. There's a distance away from the sun beyond which anything that can freeze will freeze, and inside of which only the most dense things will solidify and condense. And so inside the frost line where Mercury, Venus, and Earth and Mars are, we don't see a lot of gases. CO2, methane, oxygen, all these. Now, we have plenty of oxygen on Earth, but it's bound up in the mantle of Earth. And we have a very thin atmosphere. Our atmosphere seems, especially today, it seems pretty thick and hot, but in the oceans of Earth, there's a lot of oxygen and hydrogen in the oceans of Earth. But my wonderful students, if you look at the depth of the ocean, the average depth, or even the deepest depths in the Mariana Trench, the Challenger Deep, that is pathetic. It's not even a puddle on the surface of the Earth. It is so thin, but to us it seems like a lot of water, and it is, but on the planetary scale, it's just a skim of water on the surface. And all of our weather is driven by it, but it's not very big. And that's because we're inside the frost line, so most of those volatile gases evaporate away, and they're driven away by the solar wind. All the protons and neutrons and electrons, helium nuclei that burn off the surface of the sun outward in all directions. The solar wind causes the aurora borealis, and it causes, all these volatile gases to, move to the outer solar system. Outside of the frost line, you'll see the gas giant planets. So that's the dividing. Now, it's not some visible, like a yellow line, like when you're out on the highway, don't pass, But it's kind of a theoretical boundary, and people say, well, about 1.93 astronomical units or 2.7. What we know is that its approximate location is somewhere between the orbit of Mars and the orbit of Jupiter. Because Jupiter is a gas giant planet, so Jupiter's got it's far enough out, it's cold enough that Jupiter has a lot of those gases frozen and condensed. So a lot of CO2 ice, a lot of methane ice and stuff out there in Jupiter. Mars, too close. A little too hot. And Mars is pretty cold. But for those gases, it's kind of dicey to try to keep things frozen inside the frost line. All right, now, the frost line. It's kind of a thermodynamic boundary. All right, and inside the frost line, the only thing that can remain solid and not get blown away by the solar wind is stuff like iron, silicon dioxide, pyroxene, all the minerals that we find in the Earth's crust. They're heavy enough that they'll solidify inside the frost line, but everything else, not so much. We have some, and here's a picture of Mars. Mars has some. Look, it's got a polar ice cap. All right. 1.524 AUs away from our star, the sun. It's colder. This is our main topic, the basic specs for the planet Mars. It's got a longer year. Its spin rate is just a little bit longer. 24 hours, 0.6597. So if you were up there on Mars and hopefully one of your grandchildren might be an explorer, and some of your grandchildren's grandchildren might colonize Mars, maybe, several hundred years from now, the day would be about the same length as here on Earth, just a little bit longer, right? The axis tilt is about 1.85 degrees away from the North Star. Okay, so, and most of the spin axes for the planets except for Venus, are pretty, and I think Uranus is also tilted away from the North Star significantly. But all the other planets are pretty close to the North Star. They're not exact, but within a few degrees. And so the north side of Mars, which we're looking at here, the top of the photo, that's the north end of, or the north pole of Mars, the polar ice cap up there. That's like, parallel to the north pole of Earth. They're both looking, basically, if you were up there standing at the north pole of Mars, you'd see the North Star making little teeny circles if you watched all night. And on Earth, you'd see the North Star not making a circle because it's the pole star, but you'd see a few of the nearby stars making little teeny tiny circles, just like the North Star does on Mars. Question? How long would it take you to get from Mars to Earth? Just depends on how big of a rocket you have, or from Mars to Earth or Earth to Mars. Mars to Earth probably faster because you're going downhill towards Earth. But it just depends on how big of a rocket. But months, or more. What's stopping us from colonizing Mars is the distance and the enormous cost of putting every kilogram of anything into Earth orbit, much less all the way to Mars. It's very expensive. Takes a lot of rocket fuel. But we're working on it. Yeah.
Plus, there was a lecture from an anthropologist a few weeks ago on this, and one of the things is also we need preparation in regards to radiation.
Yeah, it's a hostile environment on Mars, but not that hostile. You'd need scuba tanks, but on the equator of Mars, it's warm enough in the middle of the day that it would feel like a cool day here in Orlando, 40 degrees. So people here from Florida would be freezing their butts off on the warmest day on Mars. But people from up north, that are used to cold weather, they would be walking around with their t-shirts off. Except they'd have to have a pressure suit. But the orbit is fairly eccentric, so that means it's significantly closer to the sun during southern hemisphere summer. All right, so southern hemisphere gets a little bit longer, a little bit more heat during its summer. All right, and so in northern hemisphere summer, a little bit longer. So you have more extreme seasons, more extreme weather, especially in the southern hemisphere. Like if you go, and here's a counterexample. When I say extreme weather variations, it's the opposite of like living in St. Thomas in the Virgin Islands or anywhere in the Caribbean. Down there, the ocean water is always about 80 degrees. It's tropical. And so the weather never gets much below 80 and hardly gets above 90 very often, except during hurricane season maybe. The humidity varies and stuff, but not the temperature. And so the ocean in there tends to moderate the weather in that part of the world other than hurricane season. All right, now on Mars, not the same. Look at this. Here's a pair of pictures of Mars from 2001. The one on the left is June 26th. And the one on the right is September 4th. Now let's see, what is that? July 26th, August 26th, 2 months and a few days. And in between those 2 days, clear weather, clear as a bell pretty much, June 26th, but by September 4th, man, that is a sandstorm. The entire planet. Raise your hand if you've ever been out in Arizona or anywhere else in a sandstorm. Anybody ever been in one? I've never been in one. But when I lived in St. Thomas down in the Virgin Islands, you know what we could do? We would sometimes observe days when we got sand, very fine sand, blown across from the Sahara Desert. The sky looked almost sparkly. It looked different. And they can measure it. And for people that are from down in the Caribbean, they know, and you can see it on satellite images. This little cloud, but it's not as big as this. It's maybe the size of a small hurricane, and it's coming, and it comes off the coast of Africa, and heads our way, and then it dissipates, by the time it gets to the United States. You know what else we see? We see similar sandstorms moving across from northern China, from the Gobi Desert, and also forest fire smoke blowing all the way across from China. But it's nothing like this. That is astounding. And that's why the surface of Mars is so red. It's just uniform. And when you guys are out there looking at Mars by eye, stargazing, eyeball stargazing, you'll know Mars because it looks red. There's a reason for that. All right? Okay, the distance. 1.524 astronomical units. That comes out to about 757 light seconds. Go ahead and jot that one down. So now some more specs. To walk around the equator is about 13,000 miles. Now here on Earth, it's about 24,000 miles. All right, so it's a little bit smaller. All right. And it's still pretty big, though. I mean, it's a fairly good-sized planet. We can see a lot of subsurface water on the surface of Mars. I shouldn't say on the surface, below the surface layers of soil. The way that we have done that is by using what we call a ground-penetrating radar mounted on the Mars Express orbiter. We got all kinds of rovers on the surface and orbiters in orbit. And we've had spacecraft fly by like Voyager and Mariner. And we have found that there's abundant subsurface water at various depths. A lot of it. A lot of water. And for those of you guys that were asking about why can't we colonize Mars, some people think that we can. If we can get to that water and liquefy it and turn some of it into oxygen for the atmosphere, maybe we can colonize Mars. But it would be a huge undertaking. Carbon dioxide. Look at this sentence here. About a third of the carbon dioxide moves from north to south poles. The South Pole and the North Pole have a lot of CO2 ice. We can see it. It looks white in the photographs, but when you look at the spectral lines, you see the spectral line of D, the quantum fingerprints of CO2 and H2O. I mean, it's not just like here on Earth, you don't see any CO2 ice at the North Pole. You see water ice, H2O ice. But up there, in Mars, you see a lot of CO2. It's kind of a combo effect, all right? And because of the weather, there's an effective transport from North Pole to South Pole. It's incredible. Violent weather. So if you were up there on Mars, there would be times when you got to duck underground, head for cover. Much worse than anything here on our planet. And Curiosity is also finding a whole lot of other signs, possible life. For instance, methane. And in fact, there's an Italian scientific team that I believe they were using either Mars Express or one of the other orbiters, and they found plumes of methane gas in the atmosphere on a temporary basis, a seasonal basis. Now what that means is they think that it's possible that there are still forms of life on Mars below the surface that generate methane. Now, there's all kinds of organisms here on Earth that generate methane. All right? It's just a regular gas, CH4. All right? And they found it, plumes of it in the atmosphere. Now, it's very hard to observe, and they haven't observed it a whole lot, but I guarantee you they're going to keep looking for it and study it, and they've narrowed down a few locations. So we're always curious about that. Now, water, CO2, methane, what does that have to do with volcanoes? Volcanoes are pretty important on Mars and on Earth, right? Because they produce, because volcanoes produce a lot of gases. You know, it's not just molten lava. You know, that floods through the city of Pompeii and kill. It was actually the gases. What they call the pyroclastic flow of gas down the side of Mount Vesuvius that killed all those people. Now, on the planet Mars, the largest solar system the largest volcano in the solar system is on the surface of Mars. There it is. Olympus Mons, they call it, Mount Olympus. And it's ginormous. It's basically the size of Arizona. Whoa. Look at it. It's gigantic. And it's a lot like the Hawaiian Islands. Now, the Hawaiian Islands are the biggest mountains in Earth. They're bigger than Mount Everest, except they start at the bottom of the sea. And they rise way up above the surface of the sea. And supposedly they're bigger than Mount Everest. But they're also the biggest volcanoes on Earth. And they're way out there in the middle of nowhere, out in the middle of the Pacific. Just a little hot spot on the Earth that blooms a lot of volcanoes. All right, and we think it's something like that here. Now, this thing's 26 kilometers tall. Now, 26 times 6, 120, 150. So that's about 15 miles high. Olympus Mons. 15, 16 miles high. That is getting up there. That is a big mountain. Thomas. You know, we don't know. We've not seen it erupt. We think maybe. And, you know, if there ever is a crew of men and women up there exploring Mars and this thing goes, oh my goodness, they're going to be really busy trying to measure everything and not get killed, you know. Because, you know, like Mount St. Helens out in Washington State, it blew up and it covered all those towns in volcanic ash, and that's nothing compared to like Yellowstone, the Yellowstone mega volcano. This makes that look like a spit wad in second grade. You know, if this thing ever goes, man.
That's what I was wondering about, because when you're talking about the giant dust storm, I was wondering if it could be responsible.
No, we're pretty sure that's not the case. We think that's weather related because it's atmospheric dust. It's not volcanic dust. Here's another view. There's the Hawaiian Islands compared to the state of Arizona. So Olympus Mons is bigger than the Hawaiian Islands. The Hawaiian Islands are still pretty big. You know, they're competitive, but Olympus Mons, it's gigantic. All right, let's do some clicker questions. Take your clicker out. Good. And let's do a couple questions about volcanoes. All right, first. Lava, molten lava. What's it also known as? Somebody voted for E. 15 seconds to vote. And try to vote. I shouldn't have put it on there. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, most of you got it right. Magma. The other stuff is just words I made up. Trogdorite. Polynesian sauce. Just don't drop the Polynesian sauce on your calculator. That's all you got to remember. Question. In addition to magma, a volcano can also emit great volumes of if you click the answer, which you can see here, if you click, then it's graded. Yeah, right. Tricia showed me how to do it this morning. So it's nice, yeah. Yeah, awesome sauce. It's almost as good as Polynesian sauce.
Almost as good.
Yeah, so that's good. That's graded now. All I got to do now is change the name to L14 PM as soon as we're done. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, most of you got this one right. Make a note of that. Sulfur dioxide, yeah. CO2, yeah. Let's keep going with Mars. Mars has a distinctive mixture of gases in its composition. Most of the oxygen is gone, most of the hydrogen is gone, most of the helium is gone from the atmosphere. And there's a lot that's in rocks and water and stuff. But in the atmosphere, it's mostly carbon dioxide, still has a little bit of nitrogen. Now, we have a lot of nitrogen, 78%, something like that. 21% oxygen in our atmosphere. Mars, not so good. All right, a trace amount of water vapor. But we know that water was in a liquid state in the past. We could see the signs of it. You know, the great big valley, Valles Marineris, the Valley of Mariner, is an erosion feature. It's a canyon. I mean, stuff that's formed by water has a certain look. We can see melted water features from time to time, you know, down small, very small, you know, like a little chunk of a little glacier the size of this classroom suddenly melting for some reason, we don't know why, and forms liquid water and drains down the side of a canyon for some reason, we don't know why. We can find rocks, and have found rocks, on the surface of Mars that form in water. Well, you know, same rocks on Earth, and we know that on Earth they form underwater. And we've seen that on Mars as well. So, and we know that there's a lot of water in the polar ice caps as well. This is a famous, go ahead and make a note of this, this particular meteorite. I think we'll talk some more about it. NWA 7034, found in Northwest Africa. We'll probably talk about it on Thursday. It's actually a piece of Mars, blown off by an asteroid impact of some kind, and blown into space, and eventually fell to Earth somewhere in Morocco, they think. All right, it's 2:50. Let's dismiss. We'll talk about the solar energy budget on Thursday. You're dismissed. I'll see you Thursday.
People are going to come for their tests.
Come up front if you want to grab your exam printouts. And I'll do, can you give me that? I'll do that if you can.
What do you need?
Just give me the pile.